Right on. Okay, so welcome everyone to the 43rd episode of the SFU Sports Analytics Virtual Seminar Series. Today we have Dr. Ron Yurko, who's going to speak to us about NFL Ghosts, a framework for evaluating defender positioning using high-dimensional conditional density estimates. Dr. Yurko is an assistant teaching professor in the Department of Statistics and Data Science at Carnegie Mellon University, excuse me. His research focuses on developing methods at the interface of inference and machine learning, oriented towards problems in natural language processing, statistical genetics, and sports analytics. He leads the sports analytics initiatives at Carnegie Mellon and co-organizes, the annual Carnegie Mellon Sports Analytics Conference. So just in terms of the talk summary, player attribution in American football remains an open problem due to the complex nature of 22 players interacting on the field, but the granularity of player tracking data provides opportunity for novel approaches. In this work, we introduce a framework for evaluating the positioning of pass defenders with regards to limiting of receivers' yards gained after the catch, which is abbreviated as YAC, relative to hypothetical defenders known as ghosts. The framework consists of two components. First is an estimate for the receiver's YAC distribution, and second, an estimate for a ghost defender's 2D position distribution. They will model both distributions using flexible, non-parametric, high-dimensional conditional density estimate techniques to account for rich features derived from player tracking data. They will then compare how a defender's observed positioning at the moment of catch impacts the estimated YAC distribution relative to the ghost defenders. By modeling the full YAC and ghost distributions, we are able to compute novel ways of assessing player positioning, such as the change in expected value. Although they focus on pass defense, they will discuss how this approach can be extended to other aspects of American football for measuring a player's leverage within a play and the difficulties in extending for continuous time assessment. So with that, I'm going to turn it over to Dr. Yurko, and it's really great to have you along with us. Thank you very much. And this sounds like a very technical and interesting talk. So we're really looking forward to it. Thank you.
All right, thank you. Thank you for that introduction and going through what is actually a rather dense, abstracted description of this work. Uh, so good job getting through all of that. All
Thanks.
right, so okay, can you see my screen?
Yep, looks great.
All right. So this work that I'm going to go through today, um, the paper is not out yet. I'm hoping to have this up on the archive optimistically by end of April, given in the semester, maybe that gets pushed into May. But so this is ongoing active work. I should mention that other collaborators on this are PhD student Kwong Wen and professor at computer science, Dr. Kostas Pelakrinis. Okay, so let's get started. We're going to work through a bit of a review in a way of thinking about the mindset that we have for evaluating player performance. And this traditional view of sports data for analysis consists of this mindset, discrete mindset, where we have some period of time along this x-axis, and we have some starting value at the beginning of period of time, and then we have some ending value after whatever period of time takes place. We observe some difference, and the idea is we want to then try to attribute this change in value to whether it be the players on the field, players on the court, whatever the sport could be. Traditional type of regularized adjusted plus minus models, taking this mindset, you have a stint, a shift where there are no substitutions, and some change in score, and you want to get a sense of what's then the value each player is attributed. Now, we're going to focus on American football, which of course has its own different complications that many people watching this are probably aware of. Football is a sport where the context really matters. So I just have this cartoon diagram, two plays on the left-hand side. You can imagine it's a 3rd and 15 or 3rd and 20, whatever it could be. And the running back gains maybe 10, 12 yards. And it's a very long arrow in red here that's indicating a nice yardage gain, but they fail to reach that gold line denoting the first down marker. Versus on the right-hand side, we have a play of much shorter length, but the blue arrow crosses the goal line, indicating that okay, this ball carrier achieves a first down. So this play on the right-hand side is much more valuable given all this context in football that we have to account for versus just the longer play that's on the left-hand side. So I'm going through things that might be review from folks watching this, but this is all to build up towards how we want to get at attribution within play with tracking data. All right, so in the traditional mindset of looking with play-by-play data, we have the context describing what's going on at individual play level within football games. So we know, was the possession team the team with the ball on offense? The opposing team is on defense trying to stop the team with the ball. That possession team has 4 downs to advance the ball to cross that gold first down line or to reach the end zone, score a touchdown. And if they advance past that first down line, they will get another set of 4 downs. Otherwise, they're going to turn the ball over to the defense. And with that, we know what's the yards to go in order to reach that first down marker, as well as this yard line just indicating to us where are they at on the field relative to their target end zone they're trying to reach. And then we can have additional context as well in terms of what's the time remaining in the game, in the half, maybe the score differential if we're thinking about the win probability that we might observe, a variety of different things we might also additionally account for, timeouts included. So this is just the basic understanding that we have, and we can view then the outcomes we might think about from this understanding of what's the expected value of the situation. And what we'll focus on here is the drive level outcomes that can take place in terms of a drive can end in no score. It can end in a field goal, touchdown, or safety with respect to the possession team. But we're not just going to model what's the scoring outcome of this particular drive. We're going to model what's the next scoring event that will take place either by the possession team or the opposing defense. So this includes then modeling the probability that the opposing team scores a touchdown next, given the context that we observe, as well as the opposing team kicks a field goal. So ultimately, we have 7 events of next score that could take place in terms of the next scoring event within the half a play of a play of interest. That's going to establish our expected value at the discrete play level, between play level. So we had previous work going into this of using a multinomial logistic regression model, where we're going to predict the scoring events and then can compute, given the probabilities of this model on the left-hand side, a simple linear representation of the log odds of each of these scoring events relative to no score. We can get these predicted probabilities, aggregate the probabilities times the associated point value to get then this expected value between plays. And so we can imagine then this can serve as our starting value for the play, given the context. A play takes place, a running back gains 5 yards, a quarterback throws an incompletion, quarterback throws a 25-yard pass, whatever could happen in between, we'll observe a change in this expected points. And this has been the simplest view of assessing performance in football so far, prior to the entry of tracking data, where we have expected points at the start of a play, expected points at the end of a play, and we just simply compute that difference, expected points added. But we want to somehow divide the credit of this value to the players on the field. But what we know is this is an oversimplification of the reality of sports. There are 22 players on the field in American football, all moving around in different complex ways. And so this value is not just a discrete starting to an ending. There's some continuous change, like a stock ticker going up and down, depending on the movements of what's happening throughout a play. And so we want to then think about how do we approach then doing this continuous time valuation. And so courtesy NFL Big Data Bowl, there have been the samples release of the tracking data that we have for football. So every 10th of a second, we know where all the players are at in the field. We also know where the ball's at, although that one's a little bit fuzzy. But we know the speed at which players are moving, the orientation that they're facing. So it's extremely rich data. that we can then try to leverage and use for how do we get within the play? What is this expected value of what could happen? So this is just an example that we used in this paper a number of years ago. It's run by Cordell Patterson when he was a wide receiver for the Raiders. And so you can see just a snapshot of the table, what the tracking data looks like. Every row is a moment of time, the XY position for Cordell Patterson in this case, the speed, the direction they're moving, and these events that the NFL provides with regards to snap, handoff, contact, tackle, ball arrival, a number of different things. And so this tracking data representation of the play, we have on offense, the blue dots, orange dots corresponding to defense. And then we have the black circle representing Cordell Patterson once he gets the ball and on this jet sweep run. So he starts on the top, receives the handoff, takes off, and ultimately scores a touchdown. So it'd be interesting to know is how do I compute this continuous time within play value? What is the stock ticker representation? Knowing that there's some expected points at the beginning of the play, ultimately this play results in a touchdown. But where do I observe the biggest changes in the value throughout this play? When do I think he's going to ultimately score a touchdown? Is it right at the beginning or is it somewhere in between? Where, and then can I think about what positioning is going to matter in this case? So from our viewpoint of thinking about getting this within play value, we can imagine what we need to do is have some prediction for the ending yard line. All right, because that's all that really determines these features that describe the expected points of a situation. That context I showed you from before, the down, the yards to go, the yard line, they're all functions of where will the play end. And so we need to somehow have effectively an estimate, this Y hat representing what will be the ending yard line at moment T within play I. And that's going to then feed into updating these features of that matrix that I have in my multinomial logistic regression model. But each of those single predictions, this is just going to give me a point estimate of what the expected points are within a play at moment T for play I. In order to get an actual proper valuation of what's this expected value, I need to recognize that this expected points is some utility function that I have. It's some complex utility function that relies on this multinomial logistic regression model. But if I want the expected value of that utility function, I need to rely on good old friend of the law of the unconscious statistician, and I need a distribution estimate for this ending yard line that I need to ultimately integrate over. So I have my play value V here, and I'm just going to think about it in terms of expected points. But it could be whatever I actually want. It could be win probability. It could be some complex utility that I'm measuring what's going on within a play. And so I have that represented by G of the ending yard line. G is this utility function that takes in the ending yard line. And what I need then is to compute this expected value of this utility. I need a distribution estimate, this conditional density estimate of my ending yard line, given what features I observe going on within the play with the tracking data. And so what we're going to rely on throughout the different pieces of this work are a random forest for conditional density estimation. All right, I'll get in a moment why that's useful in this context. But what I could effectively generate at every moment within the play is a distribution estimate. So this is showing at a particular moment, I believe when the first contact was made with Cordell Patterson, where I have two representations of the distribution shown here. So on the top, you see these red lines on the field, where the darker intensity is reflecting along the plot on the bottom, the higher conditional density estimate. And so what this is signaling to us is there's a high mass, all right, relative likelihood of the ball carrier being stopped near where they are currently at. But on the far left-hand side, we have this little bump and effectively like a non-zero probability that the ball carrier is going to reach the target end zone. And you'll see this in the type of modeling of the distribution of the yards that a ball carrier will gain. Or you can imagine you really have some complex mixture going on. You're not just going to have, a nice bell curve around where the ball carrier's at. You're going to have a skew distribution, but you're going to also have some probability of a breakthrough, of them reaching the end zone, we're scoring a touchdown. So we're going to take this approach, though, of this conditional density estimate as a non-parametric flexible way to capture different distributions for the different parts of the problem that I'm going to get to today. So far, I've just been doing review. So if you've seen this before, just bear with me. Otherwise, hopefully, this gives you a good setup and foundation for really what the contribution of the work that I'm going into today. So the tool we're using for this is this random forest for conditional density estimation. And the fundamental idea is this is just a weighted kernel density estimate. So just if you want to start at the bottom here, this f hat of z given x star, this is your basic KDE where z is representing ultimately like the ending yard line. The trick is in these weights that we compute. This is how we effectively condition on a large number of features. And so these weights that we have here, so WI, this is giving the weight for observation I for some features that I observe, X star, for a particular tree, theta T, and I'm abusing notation here. So T now is representing an individual tree, but you won't see tree notation on any other slide. So apologies for that. What this is telling you is the weight of this observation is does this observation in the data set across your n data points, does it fall in the same terminal node that these target feature values, this high dimensional vector of features that I could have describing within a moment of play for a tree, does it fall in this terminal node? And look across how many observations in your data set fall in the same terminal node of a tree for those given feature values. So if I have a single observation where there's actually 100 observations that all fall in the same terminal node, what observation I will get 1 divided by 100 in terms of a weight value for a particular tree. But if it's the only observation that falls in that terminal node, it's going to effectively have the largest weight. And then what you do is you average across these weights across your key trees, because this is a random forest, right? It's a bag collection of trees to construct these weights. And then those average weights get plugged in to your usual KDE estimate, where it's just the univariate KDE, potentially, if I'm just modeling ending yard line. We're going to rely on a 2D one for positioning. But this is a really flexible way without having to do that conditioning to actually construct a proper conditional density function, right? This is sort of a kernel trick of similarity that you could plug in, taking advantage of trees to measure that similarity that you have. And the interesting appeal of this is the fact that how these tree splits are chosen are actually to minimize the conditional density estimate loss function. So this is coming from work from collaborators in the CMU Statistics and Data Science Department, where they were doing this for modeling spatial patterns of galaxies and storms and whatnot. And here I'm taking it and applying it to the notion of modeling movements of football data. All right, so flexible, we're not making assumptions here about the shape of the distribution. We're taking advantage of kernel density estimates, where we're just weighting observations by some high dimensional features, where these weights are formulated by flexible tree-based approaches. All right, so this is the toll a day. We could do it for 1D, we could do it for 2D, and you could do it beyond. It gets a little bit more tricky once you move into a higher dimensional distribution that you would want to model. Okay, so this is then the foundation for how we can construct and estimate a distribution within a play. And so what this is showing you, this figure is this animation of within the play, what does this conditional density estimate look like as it changes throughout all of these periods of time. And you could see then on the left-hand side, as the ball carrier gets closer and closer to the end zone, this red line at the end zone is going to get darker and darker in intensity. That's kind of indicating that increase in time of the probability of Cordell Patterson ultimately scoring and reaching the target end zone. And so when we do something like this, we can then construct this full stock ticker representation of what's the expected value within a play. So we have our expected points on the top, as well as another complex utility function, win probability, along the bottom. And what we can see is how does this expected value, where we integrate over this distribution function, this distribution estimate for the ending yard line, how does it change across the entirety of the play? And seeing at what particular moments after first contact here, we see that nice bump up in the expected value. Our Cordell Patterson dodges, successfully avoids ultimately getting tackled at that moment of first contact, and really then starts to gain this increase in expected value as it becomes more and more likely that they're going to ultimately reach a touchdown. And if we put on that win probability scale, before this play, the Raiders were losing, becomes a point where, their expected value at the end is likely to score a touchdown, and they ultimately then are more likely to win just based on what's taking place within the game, within the particular play. Now, this is great and all, but the question is, how do we actually use this to assess player performance? And the difficulty of this is the models of these tracking data rely on features that are inherently functions of the player. And what I mean by that, I mean that we have things like the speed at which players are moving. We have their actual positioning. So I didn't go into the details in this prior work for this talk of like what explicitly are these features, but we have things about like the distance to the ball carrier of the defenders, right? The angles at which they're facing. These are all things that the player is ultimately determining. So I want to get a sense of how does this expected value change if I alter that the player specific features, their speed, their positioning, how they're facing the ball carrier they're opposing, right? Those are all player specific. I want to alter then ultimately this expected value line and see what happens if I replace a player with the hypothetical defenders, or maybe the hypothetical ball carrier, some type of average that I could have. That's the fundamental goal that I'm thinking about here. I'm trying to see what is actually attributed to this player relative to how they alter this expected value within a play, to then give me a sense of what's the value of their positioning, of their movement profile that takes place in the tracking data. Because these things are inherently functions of player traits. So we're going to focus on what I view as like the simplest starting point for this. And that's going to be evaluating defenders in terms of the yards after catch. And so the inspiration for this was from the Big Data Bowl back in 2021, where the whole context was about evaluating pass defense. So you have passing plays during the 2018 season. All linemen are removed in the data. So you're really just focusing on after the ball is thrown, effectively, what's happening in these plays. And so we decided to focus on yards after catch. And so what I just have for you on this right-hand side is histograms. On the top is the yards gained, where the gray-black is referring to the air yards. So the perpendicular distance the ball traveled from the line of scrimmage to the arrival where the receiver catches the ball or potentially drops it, as well as then the bottom, the expected points added. So how much value on that between play scale of where the ball is potentially caught versus where it ends, what is that expected points value that's observed? And you can see that a lot of EPA, expected points added, is generated from after the catch. So it's a meaningful point of focusing to see, okay, who is actually doing a good job at hopefully limiting this value after the catch? And what we're going to do is we're actually going to really simplify this. And I'm not going to go into the full with continuous time sense yet. I'm just going to think about how do I evaluate the positioning of defenders at the moment of catch with regards to my value function of interest. So my value of interest here is going to be expected points. And I want to get a sense of what is the impact of that defender's positioning, their velocity profile at that moment of catch with regards to the expected points? How can I assess their positioning and velocity vectors? So we're going to start with, again, this RFCDE to generate a conditional density estimate of the yards gained after catch, given the features I've observed here at the moment of catch, so X catch. This will allow me to then integrate over this distribution to compute what is my expected value of the play at the moment of catch. And so I need then this estimate of the conditional density of my yards gained after catch, given these features that I have. So this is really just modeling as before the receiver's ending yard line. They are the ball carrier. I'm going to use this flexible approach to give me a distribution estimate for how many yards they'll gain. Now, the features that we did for this engineering problem focused on effectively distance-based and velocity-based features. So I'm looking at things in terms of what is the separation between the defender and the ball carrier? All right, this could be horizontal, vertical displacement. And I'm taking the approach we did in prior work of ordering the defenders and teammates of the receiver in terms of their day to establish like a fixed ordering at this particular moment of time. Right, so like defender 1 is going to be the closest defender to the receiver at the moment of catch. And what we actually observed where I did the use of these different features describing distances, velocities of the players, information about where the QB was at the moment of release of the throw. I use leave 1 week out cross-validation analysis to assess this RFCD model based on a conditional density estimate loss function. And what I viewed was this model actually was performing best with just information describing the receiver, the QB at the moment of throw, and the closest defender. So the information that I just need then to model at the moment of catch, what is my distribution estimate, is just relying on these 3 pieces, which is beneficial for me if I want to think about how do I alter then where this closest defender is at to evaluate their positioning, because they are all that is implicating then what the shape of this YAC distribution look like for my model. So the example I'm showing you here, this is a passing play. This was Green Bay versus Miami. So Green Bay quarterback Jair Alexander, he's the dot in red, and he is tackling the wide receiver here at the moment of catch. So we have this wide receiver who's just short. I believe it's Devontae Parker for Miami. He was just short of the first down line. So the team is going from right to left in this case. So he caught the ball and was tackled by Alexander just short of the first down line and was ultimately failed to get the first down. And so when I look at the moment of catch, what does my single distribution estimate look like for Alexander's positioning and velocity profile? We see that we have this expected value of negative 0.16 corresponding to this YAC distribution estimate, which is effectively a spike right where the ball carrier is at. I'm effectively saying, given this, a very low chance that the ball carrier is going to go beyond the first down line. They're probably going to get stopped before that first down line. And so this expected value is negative, which from the defensive point of view is great. This is saying, okay, the defense is going to be more likely to score. But this is just a single position that I've observed. And what I want to know is, how does this compare to if I move that red dot around in different ways to hypothetical possible other positions of the defender that I could have? And so I want to know then, what is this expected value for ghost defenders? I've just observed this single red line, but what happens if I move Alexander around in different ways? And so this figure I'm just showing you, I removed Alexander. This is just the context that I have at the moment of catch. I have their teammates in orange. I have the offense in blue. And what I want to then do is ultimately then model what I believe is a likely location of my defender, given what I've observed at this moment of time. And so what I'm displaying for you here is a 2D CDE estimate for the 2D location of the defender, given the information I have about the receiver. And so I looked at modeling in a similar way of information about, at the moment of catch, the receiver, maybe the defender's teammates. And what really ultimately just was the best model of this 2D distribution estimate was, what is the receiver doing at the moment of catch, right? And I just want to back up and just say, again, I'm only focusing on the closest defender. So it's a naive representation, but this is going to allow me to effectively place a value on the defender being at their particular position on the field with a particular velocity vector. And so what you see here then, this 2D estimate, yellow is corresponding to a higher density estimate of the player being observed at that spot. And then we have it going into dark blue for lower density estimates on this 2D grid. All right. You don't see something that's a well-behaved Gaussian. All right. It has sort of an odd looking asymmetric distribution. Right? And that's not necessarily surprising when thinking about the spatial distribution of where players can be positioned. So I view this as also more of a justification for why these flexible techniques are going to be required for modeling the movements of players on the field. And so I have then this 2D grid of where my distribution of ghost locations effectively. I'm not just going to model a single ghost. I'm going to model a distribution of where they could be. And so I have, again, a reminder, my expected value at the moment of catch. It takes in this utility of the ending yard line, G of Y, and this conditional density estimate of the ending yard line, given the information I have at the moment of catch. And so what I'm now going to do is I want the expected value for the ghost. And so what this will require is integrating over this 2D density estimate for the ghost location. So I have two conditional density estimates. I have one for the yak I talked about before, and now I have this second one from the previous slide. That's the 2D location, this f hat of L, and I'm just using this L to represent the XY tuple that I have, just to make it not too much of a disaster notation. And so the idea then is I'm going to generate for each 2D location new ghost features with this X tilde of L. And now with these X tilde of L, I'll be able to integrate over that to get what's the expected value for the defender at this L location. And then I integrate over that 2D distribution estimate to get then my expected value of a hypothetical distribution for the ghost defenders. Now, the caveat here is this is just modeling the location. I also should account for the velocity vector information, so the speed at which the defender is moving and the angle at which they're moving. Now, I'm going to simplify things. Instead of doing another conditional density estimate, I'm just going to rely on sampling. All right, so the idea here is for each 2D location, I'm going to sample B velocity vectors from the observed data set of the closest defenders. And that's going to allow me to integrate over potential velocity vectors that I have. And this is adjusted. So the benefit of doing just for the closest defenders and the features are characterized in terms of the relationship of that defender to the receiver. So it's preserving, if I move them around, it's still like, how is their direction changed relative to the receiver? So it's not then going to lead to some strange values, right? So it's a realistic then values that get plugged in, but I'm just going to sample over those to draw then what my distribution of velocity vectors could be in terms of their speed, direction, and angle of orientation. And then just do my similar process, integrate over the locations, ultimately then average over these samples and get then my hypothetical value for my ghost defenders. And so what this leads to is now I have this expected value grid at this moment of catch. And so what I could see is the receiver is this blue dot that's behind these individual points. These individual points are reflecting the different 2D locations on a grid of where that defender could be. Darker blue corresponds to good for the defense, lower expected value for the offense. And so you can see that the darker intensity is closer to the receiver. As you move away from the receiver, the expected value increases for that offense. And again, it's going to increase in an asymmetric way. The size of these points then are corresponding to the intensity from that plot I had before of what is the 2D density of being in the location. So the higher, the larger the circle, the more likely the defenders are going to be observed at those locations. So we can imagine now this is giving me a sense of, on a 2D grid, what is the value of being at a particular location, where I've also just averaged over the velocity vector information that I could have. And so then what we could do is then see, it's like my slide's taking some time to change here. Oh, there we go. Okay. So what we could do then is we could see, how does the defender's expected value in red here, their observed positioning and velocity vector, how does it relate and compare to the hypothetical of the ghost? All right. And so what I'm saying here is, okay, the observed value ultimately of the defender is this negative 0.16, versus the ghost distribution expected value is actually positive. It's 0.77. So it's more beneficial slightly on the offensive point of view. And what this difference is telling me is the value that I have from Alexander being at this position with this particular velocity vector is I'm putting it on a point scale. It's now this negative 0.93 value. That is the value I'm describing then for the defender for being at this position relative to what I'm imagining is a distribution of possible other positions for the defenders and their velocity vectors. And so we can accumulate this change in EPV value at the moment of catch across the sample of data that we have. And this is just a leaderboard here, giving you a sense of what's going on here, where this column, the sum and the change of these EPVs, we can see that what this approach is indicating is some of these top corners for their positioning at the moment of catch can be effectively worth almost a touchdown saved over the course of the season of data that we've observed. Their value that I'm attributing to them relative to hypothetical defenders is worth almost a touchdown over the course of a season. Now, there's some caveats to looking at this. All right, the ball has been caught, so they've done something wrong already, probably, to be in this spot. But I'm just trying to get a sense of what is the point value worth of being at this spot at the moment of catch. And I can compute what's the average over the course of the receptions that they face and see how it relates to the yak, the yards allowed. And so one thing that we looked at here along the x-axis is this average change in EPV for defenders at the moment of catch, facing at least 10 receptions. And the y-axis is the average yak allowed. So the interesting thing, again, about this is I'm modeling this at the moment of catch. My EPV, change in EPV, it doesn't care about what the outcome of the play was. It's just saying, what is the hypothetical distribution that could be observed at the moment of catch? And what's that difference in the value between the defender and what the distribution of ghosts could be, agnostic of what the outcome actually was? Now, the y-axis here is really the outcomes that are observed on the yards after catch scale. So what's not surprising is, of course, there's a relationship here between the average change in EPV versus the average yak allowed. Players that, okay, they're doing better than the ghost defenders are more into the bottom left, and they're also limiting the actual observed yak. We do see some positional bias going on here, though. I don't have position in the 2D CD model, and there could be justification for including that, as defensive backs tend to be much better in terms of their positioning at the moment of catch relative to the yellow dots corresponding to linebackers. Now, we do see some linebackers jumping out. I'll have to check to see where the names of these players are, but there could be motivation for doing some adjustment within the model, but we can also imagine some post hoc separation of within the position averages as well. And just to get a sense of also like how does this relate to more aggregate levels of team performance, I have two plots here. On the x-axis on the plot on the left is at the team level, what is the sum of this total change in the EPV at the moment of catch for their observed defender positioning, where then the y-axis is just an aggregate defensive expected points allowed effectively on just for passing plays. So this is a combination of the yards, travel, completions, yak, just an aggregate level team pass defensive measure. And what we see is we actually observe like a moderate correlation here, about like 0.4, between just our change in EPV at the moment of catch, where the bottom left is the best thing here. All right, from the viewpoint of negative expected points added is good for defense. And so just our change in EPV at the moment of catch displays a relationship with just aggregate measures of how well was this pass defense performing. And on the right-hand side is a similar viewpoint, except for the average level of average change in EPV and the average EPV for just the aggregate team defense over the course of the whole season. So this information about at the moment of catch and what's observed for the defenders appears to then just be related to then this aggregate level measure of team defensive performance. Now, there's a lot of limitations to what I've gone through, all right? The main thing is I've started with a framework now for thinking about from our perspective of evaluating the positioning and velocity information about a player on this point value scale. Right, and we're relying on a flexible CDE approach for this. Now, I have to recognize that I can't just attribute all of this EPV change solely to the player. All right, they could be in that positioning due to whatever the play call could be, the scheme of the team, the coaching staff. It's not necessarily just due to that player. I'm also only considering the closest defender. All right, so this is conditional on this distance and information about the receiver. But should I actually think about modeling the ghost team defense together? I'm only focusing on one player, but I can imagine there's probably value in thinking of how do I evaluate a team collectively? That's going to be a much more difficult problem. I'm also only just focusing on yak. So I'm doing this conditionally at the moment of catch, which means the pass was complete, meaning something was already wrong to get to this point from the defensive point of view. Now, could extend this approach to thinking about prior moments in the play, but that's going to require the additional models for, say, pass completion model, target probability model. Different components that I know folks here at Simon Fraser have also worked on. You can imagine we're going to propagate them, these ghost distributions throughout those different models. It's going to require a lot of effort. And I've ignored the whole time here this continuous time part. So here's another play that this is, again, the red dot is Alexander. And what he's trying to do is hit, at the time, this was wide receiver Adam Thielen for the Vikings, this pass by Kirk Cousins. And how do I do this approach in full continuous time rather than just at the moment of catch? This is the question I really want to think about moving forward. And one of the difficulties is Alexander is not the closest defender throughout the whole play, right? He's just the closest defender at the moment of catch, but then he fails to make a tackle, and then there's other defenders here. So the way I approach this problem is not going to work necessarily from like a clean interpretation viewpoint. But I could imagine here is my full continuous time EPV for this play. All right, from the moment the ball is caught to ultimately where the receiver was tackled. And so it starts with some expected value below 2 and ultimately reaches a point where they avoid that first tackle by Alexander and then ultimately get tackled after a certain point and gain some yards. The red line is what I can imagine if I take my approach and do it in continuous time. So this isn't a hypothetical red line. This is me actually doing this process of at every 10th of a second within this play, let me replace the closest defender with a distribution of closest defenders. And so I could see here, I have this red line indicating to me then, where's the expected value for the ghost, where at the beginning, the red line is above the observed blue line, indicating that the positioning and velocity vector information of Alexander at the beginning was probably very good. But then he misses the tackle, so the blue line goes above the red line. This is where the miss is in the value, the spike here. This is what was lost from the defensive viewpoint. And ultimately, then the closest defenders that remain follow along this hypothetical ghost distribution. Now, the challenge, though, is it's at this player role level. I have players that are the closest defender, and that changes potentially throughout the course of a play. So I have to think carefully about how do I want to actually move forward with this concept to extend it in continuous time. Do I have my feature engineered in this role, or do I do it player specific? And that's going to require more careful thinking. But fortunately, moving forward, I'm going to have Kwong Wen. This is going to be a larger focus of his research, of thinking about this continuous time ghost evaluation. And so I just want to mention this work's possible. Again, Kwong and Costas Pellecrinis, as well as conversations with Sam Ventura and Nick Damaso. He's one of the people behind these random forest for conditional density estimates. And keep posted. This URL will eventually be updated in the weeks ahead for our conference upcoming in the fall. But with that, I've talked enough, and please let me know if you have any questions about any of the work.
Great, thanks, Ron. That was very good. So yeah, we'll hopefully you'll get lots of questions from the audience. Got a knowledgeable crew here, so if you want, you can either send it to me in the chat, or you can unmute yourself, turn on your video, and ask away. So I'm going to start with Dr. Tim Swartz, who's offered to ask a question.
Hi, Ron. Thanks for the talk. Lots of interesting ideas there. I'm wondering if you could just repeat for me or explain a little more the distribution associated with the location of the ghost defender. I'm thinking that where you are depends a lot on what's happened, some time in advance of the catch. Anyway, could you just tell me a little bit more about that?
Yeah. So this it's a great question. So what I only have looked at so far was using information that's observed the moment of catch. But this is an interesting question from the viewpoint of what is the relevant information to condition on, to think about what the hypothetical could be. And I can imagine comparing to, say, given information at the moment of throw, what does the 2D location look like for the defender instead? I only looked at possible information at the moment of catch. So I looked at, if I condition on information about the receiver at the moment of catch, as well as the closest defensive teammates. I looked at adjust at the moment of catch all those different players that could be accounted for. And effectively the best model was the one that only relied on the receiver. But different time points are probably going to implicate different shapes of these distributions. And I haven't done it yet, but I'm under the impression that I would imagine that if I said condition at where is the defender at the moment the ball is thrown, to model what their distribution could be at the moment of catch, it gives me a different sense of like the change in value, right? Because then that would be crediting what they did relative to where they started when the QB made the decision. I feel like I'm rambling a bit probably in a way, but I think the important thing is of assessing where you think it matters what you should condition on. And I don't have a good answer for that yet. I think I need to do some comparison of how does this distribution change if I only consider information at the moment of the throw. Maybe if I only consider information at the moment of throw, the distribution is wider. It's probably more variance and what we would expect players to be located at. Versus at the moment of catch, it's going to be heavily concentrated around that receiver position. Yes. So sorry, I don't know if I answered your question, but it's something I've thought about in different ways.
Okay, thank you. That's great. Okay.
Okay, thanks, Tim. Any other questions? Just maybe while we're waiting. So, uh, and I guess when you're picking the closest defender, it's not necessarily going to be the defender who's actually covering the receiver. Is that fair to say? And
Yeah, that's 100% correct. I mean, it could be. There's the caveat that maybe there's two defenders right next to each other, and the one that was actually assigned with recovering the receiver wasn't the closest. And one could approach fixing that issue if you had some process of like identifying via some approach of who you consider to be the defender assigned to receiver, and only then focusing on them and modeling their hypothetical positioning and whatnot. But yeah, it's the caveat too, is I'm just relying on what was observed with the distance.
And so, pardon my ignorance, like I don't follow football terribly closely, but I mean, to what extent is there double coverage and in different strategies? Like just just as a general question, not necessarily as a criticism or a question about your method, but like how often would a wide receiver or other typically pass receivers be covered by more than one defender?
Yeah, that's a good question. I don't think necessarily like throughout the passing play, but after the ball is thrown, you'll see a convergence of like defenders that could have been in like a more zone free roaming role, then swarm to the ball effectively. And for the most part, if there's man coverage, there's one defender on the receiver. So it could work out easier in a way if I'm just like modeling a single defender covering a receiver throughout a play. If you can imagine, like what is the value of their pass defense in this coverage? But there's going to be examples where potentially multiple defenders converge on them. But usually, I think it's just primarily one. If someone, I have a feeling there's people on this that are much more knowledgeable about football than myself that probably can jump in and correct me if I'm wrong about it.
Yeah, I don't know. Don't give us too much credit. What is the could you like actually, I mean, presumably extend your method to, assessing zone versus man-on coverage, as a defensive scheme against certain opponents or for certain teams and their ability to defend?
Yeah, absolutely. And one of the motivations for why I actually approach like modeling the distribution of the locations in this 2D fashion was not knowing what the coverage type is, right? Because my viewpoint initially when we started this, I was just doing like a point estimate of like, oh, this is the ghost defender location. But then some of the times I would get some strange locations of the defenders if I was just predicting a point estimate. And what I realized is there was almost like a multimodal structure going on where there was like a defender right on top of receiver and then almost like a zone defense that was kind of picked up. And so that led to, well, actually, it's a full distribution of what could take place. The average might fall between man and zone. So how about I carefully model the 2D location and the 2D distribution instead? But if I had some approach of conditioning on man versus zone, I would imagine I could have the hypothetical man coverage distribution versus the hypothetical zone coverage distribution. And then you can see, okay, what is the expected value of those two different styles and have a comparison on that point scale. I mean, that would be an ideal approach if you have that information. You could rely on, if I want to integrate over another random variable distribution, like a probability of the two, just to add to the layer of complexity. But if one had PFF data, presumably that could be accounted for.
Excellent.
Yeah, great question.
Thanks. And you talked about catches not made. I mean, could you flip this around and evaluate QBs and their ability to find receivers given certain coverages?
Yeah, it's an interesting question. The thing I've just thought about from this is like I I'm just only presenting this approach for this yak case, but I think this is the this is a general idea for how do we replace the tracking data that was observed for a player with hypotheticals. And if I want to do it for QB, um, part of the hypothetical could be where was the QB attempting the pass,
Mhm.
right? The speed at which the QB threw the ball, right? All of those are then what I would want to evaluate the QB relative to, right? Because I want you, this distribution is trying to reflect like the average defender for whatever that means, right? It's a strange average. It's a location and velocity average. But if I want to have the key thing of getting it on this expected value scale requires these distribution estimates. And it could be for a QB, the distribution in which they could have thrown the football, when they would have thrown the football, all of that, I'd imagine would go into how do I evaluate like the QB's throwing decision, not necessarily the ball arrival position. That could be another step to it.
Mm.
Uh, this is a long-winded answer way to say, I think for every position, every role, you could do this type of approach. The how much modeling though that it will require is going to just increase in difficulty. The
Yeah.
yak was sort of the easiest starting point.
Yeah, yeah, no, totally fair. So, like, I mean, ultimately, the idea of like this is like a counterfactual analysis.
Yeah.
Yeah, right on. Okay. Well, I'm out of questions. Does anyone else have any more? Well, looks like you did a great job of explaining yourself there, Ron. Oh, we do have one from David. Please go ahead and ask away.
Hey Ron, yeah, great talk. Thanks for giving that. It's interesting. You mentioned how with this year's Big Data Bowl about tackling and your presentation today about evaluating cornerbacks, is there, do you think there's a converse or contrapositive relationship that could be done for offensive players' evasiveness if you're looking at yards after catch based on the defender? Is there something that we could do for example, the Oakland Raiders receiver to say, oh, Cordell Patterson didn't or had a at that point could have been tackled but was not, and therefore credit be assigned, or is that too complex with blocking and other things to really
No,
make a one-to-one
I think
relationship?
it's a great question because you can imagine, this EPV change I have is just at that moment of catch, but there's still the rest of the play that happens, right? So if I'm saying, oh, this defender is in such a wonderful position at the moment of catch, but the receiver still beats that defender and ultimately has a great yak or whatever it could be. That would give me more weight in indicating that the receiver did an even better job than probably expected, right? And one of the things we've been thinking about with this approach is thinking of like this change in EPV as almost a leverage of saying how much importance does this player have at this moment of time. Because if I change a player around and they don't shift this expected value, this expected value, it's like, well, that player is not really contributing to the play, really. But here I'm saying, oh, this defender, it could really shift and change the value. And it makes sense to the closest defender. So they matter more. But I would, in order to sort of answer that question about like evasiveness of receiver, I could connect it to the actual ending play outcome of saying, oh, this is what was observed given the defender's positioning. And I can assess then, well, they beat even a top quality defender, right? I have some numeric scale of saying what that coverage was at that moment of catch. And that could give me more of a signal of separating potentially receivers. Or you could do it this hypothetical distribution of receivers too at the moment of catch. How does their velocity vector information change, and evaluate that even potentially in continuous time? Yeah. Yeah, great question.
Cool. That sounds good. Thank you.
Thanks very much, David. Anyone else? Tom? And then Matt after Tom.
I I actually just wanted to comment mostly on David's question, and that was it 3 years ago, 2 years ago, the Big Data Bowl focused on punts and punt returns, and the winning team happened to be from SFU, and they did more or less exactly what David was asking about. They looked at how punt returners were able to look around the field. They put velocity vectors on every player on the field, and including blockers, and tried to identify the optimal path that would avoid the most blocking or the most tackling, and looked at how good different punt returners were at identifying the optimal path, and then also, given the optimal path or given what path they did take, maximizing the yardage that they could get. So it didn't use any of the random forest techniques that Ron was talking about. It used a completely different approach. But I guess in one sense, there are very, 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 very many ways to crack extremely complex nuts. And none of them, all models are wrong, some are useful. None of them are solving the problem completely. Ron, go ahead, Ron.
The great work, Robin Ritchie and crew. Is that the one you're referring to, right? Yeah. The optimal pass through. Yeah, it's another approach for imagining. Yeah, try to get a baseline of comparison, right? How far away was this path from this approach from saying what is the optimal path through the return? And it's a way of saying what is this? How much worth? What value does this observed tracking data have for the player? Yeah, and that was another approach for getting at the same type of idea, right? What is the value of the observed tracking data for a player relative to some approach for getting a baseline?
Matt, did you want to chime in?
Sure. Thanks, Professor Yurko. Nice to hear from you again. Very, very professorial in your conversation, because every time I had a question, you answered on the next slide. So congratulations on having your material in order. Always a fan. Would love to bother you a bit, though, about the distribution, get a bit of a better understanding about what levers are being pulled and what levers could be pulled in like a more complete data sense. Because it's 2017, you have like what, 6 weeks, 8 weeks? I can't remember what the actual span.
I think it was a full season, but only passing plays.
Oh, okay, yeah. So when we're talking about the distribution, in this case, the levers that are being pulled is like you're moving the X and the Y for the nearest defender, and then you're sampling the other vectors associated with them, the velocity, the orientation, and those components, right?
Mm-hmm.
And then you'd given a bit of a brief mention about including position, and something that was not included in this first version, but something that could be included in an iterative example of this, like an enhanced version down the road. Like what other features here would you deem to be useful in the context of describing a distribution of defender locations that couldn't really be fit into this first version? Because when I was looking at the list of the top players, I saw a lot of DBs, not as many strong safeties, not as many linebackers, and I'm starting to think that there might be a correlation with the location on the field in which they typically engage in nearest defender allocation that is influencing the amount of value a player is able to earn over the course of a season.
Yeah, this is a good question, because I think I actually did look at like field position context, but it may be a thing that I really actually just don't have enough data for it to be sort of yielding an optimal estimate of those distributions. I think the simplest thing is condition for when I want to model this 2D distribution location of the position, like the XY. I'm going to be confusing here. Like I want to condition on position, the player position, right? And that's sort of an easiest starting point that can be accounted for. I mean, it's tree-based approaches, all right? We could have different categorical variables encoded in various ways. So that could be baked in as well. But yeah, some of that additional play context, I do think is going to matter because that's going to reflect like the scheme or the play call. In this version though that I did, it didn't improve anything or beyond what I just saw with only conditioning on receiver. And it's probably because of just the smaller amount of data I'm working with here. But yeah, like to your point of, where they're at on the field, whether it's at like their own 10 versus the opposing 10, it's probably going to make a difference on what that positioning is going to look like, as well as, something like personnel package information, just knowing who are the other teammates that are there, the other types of players that are there. Again, that's going to be something with like many possible levels of the categorical variable, and whether or not I'm actually going to get a better density estimate for just like the sample that it has, I'd probably question. And, one of the things that's true is like one could imagine imposing more structure on these location distributions. Like I'm taking the flexible approach of, I don't know what's going to look like, but I'm going to do a KDE effectively and be non-parametric about it. But you could maybe decide, all right, how about I represent it with some particular assumed distribution shapes? And maybe that could do a better job for me of hopefully being more computationally tractable. Because there is the caveat to all of this is a type of KDE approach to do this takes a lot of computation time, right? Because you need to rely on all of your data all the time to get the estimate of these densities. And to do that then within play continuous time is just going to build up and add even more. And so for this approach, I don't necessarily even think it's the most practical yet. And there's going to be, I think, tricks to rely on in the next steps to make it more computationally feasible too. But to your point, like I think the information about just like where the target player of interest fits within a scheme of a play is probably what I want to condition on. Like I want to evaluate how this defender is doing, knowing this is the type of play call. Because otherwise, what my value could be attributed to is this was the better play call that put them generally in the right spot, generally moving in a certain way, versus, given that this is this is the particular play call, how well did they do? And if you had access to the different types of maybe charted information that could help with it, or whatever is recorded internally, personnel packages would probably be a reasonable starting point, though. Yeah, good question.
Excellent. Thanks for entertaining it. Giving me a lot to think about. And also, congratulations on being the person to probably watch that Cordarrelle Patterson run more than Cordarrelle Patterson himself.
Yeah.
Thanks, Matt. Lucas, did you want to chime in?
Yeah, hey Ron, that's a great presentation. So I also have a related question about the defender location distribution that you showed earlier. So I guess you're trying to condition in basically on the same location of all other players, just by changing the nearest defenders, right? So I'm just wondering, so if there's another offense player who's trying to block, so I suppose that will also kind of try to change the defender location distribution here.
Well, yeah, it's just a great. So like right now, like the model that I ultimately selected to use for this, the YAC model, it only relied on information about the receiver, the QB, and the nearest defender. Okay, so in that naive model, the teammate that could be in the path is going to get ignored for what the YAC hypothetical could be. Now you're right, though, that's probably a stupid model from the viewpoint of like reality. But at least from just like what I could assess in determining what is the appropriate best model with the type of features that I have, that not including the closest teammate, was more optimal. Now that's not to say it's the right thing to do, though. You can imagine if I had more carefully engineered features, maybe something that recognizes like the path between defenders and potential blockers, that would hopefully lead to a better model that would say the teammates do matter in what the yak distribution would look like. And the other caveat is it's only at the moment of catch. So maybe at the moment of catch, we don't do as good of a job with understanding how the teammates are moving. But then throughout the course of a run, knowing where blockers could probably be very useful and informative. Now, that's why I do think more carefully engineered features that could capture potential blocking and the path of movement that could take place would emphasize the importance of other players. Now, the approach still is going to be the same idea, though, of like, who am I going to replace within that model still? But there is caveats to that of like, a teammate probably is only moving in a certain way because the defender is reacting a certain way. So if I move around a defender, the teammate probably is not going to be fixed, right? They're all correlated with each other. So it would require probably like more careful joint modeling of what players' movement could be. And I haven't tried tackling that yet.
Got it. Yeah. Thanks, Ron.
Okay, thanks, Lucas. So we put him on the hot seat here for a good while. So I'm going to end the questioning now and thank him very much for a great talk, and thanks for entertaining all the questions. So thanks again, Ron.
Yeah, thanks for having me. Fantastic questions, and feel free to just reach out any other questions or comments. And great seeing different folks, and hopefully I get to see you all at end of September at Cassis.
Yeah, that'd be great. Okay, take care.